Hi, everybody, and welcome. This is the KCP-Edge demo day. Today is March 2nd, 2023. We have two items on the agenda today to talk about. Jun Duan, who's an IBM researcher, will be showing a presentation regard to scalability challenges for ArgoCD. And secondly, we will have Kevin Roche, who's also an IBM researcher, who will be showing us an exemplar workload with using the OpenAI GPT to fuel the changes in declarations for workload placement across a Kubernetes network. So without further ado, we'll get started. June is going to go first. So this demo day is representative of works that are being done by the KCP-Edge community. KCP-Edge community you can find at kcp-edge.io. If you want to join us in our quest to create a state-based management offering platform that allows you for workload placement using filtering and allows you for rollout control, and do this all consistently across heterogeneous edge locations in a scalable manner. So without further ado, June, please.
Sure, let me share my screen. We recently have some quantitative study on ArgoCD scalability. So we are happy today to share what we had with the audience. Just some short introductions. My name is Jun Duan, and this work is done together in a team with Paulo and Andy, and we are from IBM Research at Yorktown Lab, which is shown as my background. First, I want to talk a little bit about what motivates our study. We are working in the context of edge computing, where we often have to manage a lot of edge locations, a large number of edge locations. Because the number is large, we have to consider the scalability issues. And also, the edge locations often, if not always, run customized workloads. And this customization imposes further computational requirements on the automations. And ArgoCD, as one of the automations, must take scalability into the consideration. And that's why we are doing these experiments here. In this abstract page shows the summary of our work. In this work, we study how to handle as many as ArgoCD applications with reasonable performance. In terms of performance, we care about one single parameter, which is the syncing delay from the changes at the upstream Git repository to the downstream, to the resources, which is deployed by ArgoCD at the downstream Kubernetes clusters. We have several findings. First, we have seen that with thousands of applications, the CPU of the machine which hosts ArgoCD easily becomes a performance bottleneck. And we tried several ways to handle this issue. We try to reduce our computational requirements. We try to provision more computing power, and we also change our expectation on how long we want the delay to be. In our experiments, we finally managed to sync 10,000 applications in less than 40 minutes. This picture shows the block diagram of our experiment. We host our Git repositories on GitHub, and we run our ArgoCD as well as downstream Kubernetes clusters on AWS. We use Cluster Loader, which is the community tool to load our large number of applications, ArgoCD applications, into ArgoCD server. We use Prometheus and Grafana to monitor the metrics. We also have a homemade ArgoCD plugin to work with our custom resource. And in that ArgoCD plugin, we have a switch to disable or enable customizations. That's all the important things about our experiment. We have several stories to share with the audience. Actually, 3 stories. The first story is how we hit the bottleneck of CPU. It turns out that CPU can easily become the performance bottleneck when we have, especially when we have customization in use in this ArgoCD plugin. So we have 2 scenarios in the first story. I have 2 slices to show the 2 scenarios. When I change back and forth, you can see that the only difference between the 2 scenarios is the number of replicas of the repo server as highlighted here. So in the first scenario, I have only 1 replica for the repo server. And in that case, it took 52 minutes to think the 2,000 applications. And then I increased the number of repo server, the replicas of the repo server from 1 to 3. Then I get a shorter time, which is 39 minutes. But if I have 3 replicas, I can reasonably expect the time to sync to reduce to 1/3, but that doesn't happen. The reason is that here we hit the CPU bottleneck. We can verify that by take a close look at the CPU usage of each replica of the repo server. Here, we can see that each replica of the repo server roughly uses about 400 millicores. But in the first scenario, the one single replica use more than 800 millicores. In the second scenario, the replicas couldn't use as many millicores as in the first scenario, because this small virtual machine only have 2 millicores, only have 2 vCPUs. That's why we haven't we couldn't reduce time to 1/3 comparing to the first scenario. We check the dashboard and find that CPU is almost saturated. So this is the first bottleneck we hit in our experiment. In order to handle that, we did 2 things. First, we just switched to a more powerful machine, which has more CPUs. And then we identified that the customization inside our ArgoCD plugin consumes a lot of CPUs. We have the switch, have a binary switch in that plugin to disable or enable our customization. We tried to disable that, and then we observed a considerable decrease in the CPU usage. So we also did that in order to handle this bottleneck issue. But that's the end of the first story. And then let's talk about the second story. The second story is about the default resync period of ArgoCD. We know that ArgoCD has a default 3 minutes resync period. For every 3 minutes, ArgoCD tries to make sure that the Git repositories in the upstream and the resources in the downstream are consistent. It did that in a 2-step process. First, it runs a reconciliation cycle to make sure the upstream Git is consistent with local cache. And then the second step is to sync the local cache to the downward Kubernetes clusters. In this scenario, in our story 2, we only want to check the resync period to make it simple. We actually didn't introduce any change to the upstream Git repositories. That means in this story, the scenarios in this story 2, we have only one work queue, which is application reconciliation queue That is about the consistency between the upstream Git and the local repository, local cache. We will talk about the second queue in story 3. So we also have several scenarios in this story. And if we compare the first two stories, we can see the only difference between the scenario is the number of applications. In the first scenario, we have 2,000 applications. And in the second scenario, we have 6K applications. And if we look at the right-hand side, look at the graphs, we can observe two things. First, we can see that the height of the peak equals to the number of applications, which is pretty straightforward. The second thing is that the peak is wider in the second scenario, meaning that it takes more time for the controllers to join the work queue. And if we further increase the number of applications, we can observe the peaks become even wider. And in addition to that, if we look at the lower part, which is CPU usage, we can see the peaks begin to overlap. For example, at 1437, the two peaks begin to overlap. We compare these two figures, I can see it begin to overlap. If we further increase the number of applications, actually, there are two things between these two scenarios. The first difference is that we increase the number of applications from 8K to 10K. The second thing is we change the workload of the applications. In this scenario, we have the workload of the applications roughly 2 kilobytes, but in the next scenario, we have some of the applications have a heavier workload. By making these two differences, we can observe that the controllers were not able to even empty the work queues. So that means we have hit the default resync period, hit the bottleneck of the default resync period. So the solution of that is we just increase the resync period from 3 minutes to 6 minutes. Right? That's the only thing we change between these two scenarios. And after that change, we observe that the controllers were able to periodically empty the work queue again. So bringing the work queue back to normal.
Can
That,
I have a question?
yes.
For the first scenario, can you just say in one word, what is the customization plugin doing? What is the customization it's doing?
First, I have to say in this story 2, customization is turned
No,
off.
in the first story, you mentioned that it takes a lot of CPU, and you.
Yes.
What does it do?
The customization in the first story is to do the wrapping for our custom resource, the config spec custom resource. It takes the native Kubernetes objects as inputs and wrap them into config specs. That's the simple thing it does. I didn't expect it consume that much CPU, but when we have thousands of applications, it turns out that's the major consumer of CPU cycles.
Okay. And the second question, on the other story, you mentioned that the resync is why do you do resync every 3 minutes? Usually the resync is to catch, we had this big argument last community call, but
That's not the
usually the
resync he's
default
doing. That's not the resync he's doing.
This is a different thing.
Okay.
Yeah, this resync is a different thing. I think.
Okay, so it's not the Kubernetes resync of getting events
no,
on
it's
all
not.
the exits. Okay, thank you. Thank you.
Yeah, it's ArgoCD resync. They use this term to refer to the activity that just bring the difference between upstream and downstream, if there are any.
No, I understand. So you are trying to drain the query. I understand. I was confused by the terminology. Okay, thank you.
Yeah, that's the term they use. The last story is about our record. We actually were able to sync 10,000 applications in less than 40 minutes, and we did a little bit search in the community and find that this is maybe the best result when we did our experiments. So I want to share this story with the audience. So recall that in the story 2, we only have one work queue, which is the work queue for checking the inconsistency between the upstream Git and the local cache. And now in scenario 3, we want to be more realistic by simulating there are changes in the upstream. So there will be another work queue, which is the application operation processing queue to this work queue. What this work queue is to sync local cache to the downstream Kubernetes clusters. So we have 2 work queues in these stories. We want to put some stress on our system. So we simulate an extreme scenario where all the 10,000 Git repositories make changes simultaneously. And in that case, we want to see how much time does it take for ArgoCD to deliver all the changes. We begin with a smaller number of applications, which is 2K here as our baseline. Here we can see from the right-hand side that it takes less than 10 minutes to sync 2,000 applications. And then we increase the number from 8K. We can see that the time taken being increased to roughly 30 minutes. And also we observed that the work queue is hardly emptied because we only used 3 minutes resync period. And then in the last scenario, we use 6 minutes as the resync period. We use 10K applications. We use the mixed workload. We introduce changes to the upstream simultaneously. And finally, we got all the applications synced in less than 40 minutes. So that's the last story I want to share with you. We also write a blog post to catch all the details of the experiments, and it is published on Medium. So if you simply search sync 10,000 ArgoCD applications with Google, the first result should be shown in our blog post. So you are more than welcome to visit the blog post and discuss with us. Next, we want to introduce our work around KCP-Edge, and Andy you may want to chime in to talk about this. Hey, Andy,
For your presentation. Appreciate that. Yeah, so if you scan the QR code there in the upper right-hand side, you'll get to our repository where our community is interacting and working on issues and pull requests related to things like placement, scheduling, customization of workloads, and the status summary to work at scale across a distributed state management system. Well, it is Kubernetes. So we're looking to cover as many edge locations as are possible. We're experimenting with large numbers, and ArgoCD is one of the components that we believe will be useful in the future to push this boundary. And so once we get past these initial hurdles having to do with some of the items that we've pointed out here in this demonstration, I think the next logical thing would be to see where other bottlenecks might occur within the platform. So we'll see what that looks like in the future. But Jun, thanks very much for guiding us through this presentation. Appreciate it. All right, so once we've established this large scale, well, what are we going to deploy across it? So we have Kevin Roche, who is also from IBM Research in California, Almenden's office, the Almaden office, and he's joined the community and has donated a sample workload that he'll describe and shows how it can be customized to be deployed different regions, different locations, based on parameters that can be configured using, of all things, something that we've seen in the headlines recently, ChatGPT, the underlying technology, the OpenAI GPT model. And so one of the models that they have. And so with that, I'll let Kevin take it from here.
Okay, first of all, can you see the screen? Okay, I have a large monitor and it sometimes messes up sharing.
Yes, we can. Thank you.
All right. So thank you for the introduction, Andy. As he mentioned, I'm a researcher out at our Almaden lab in San Jose. I am most of the time in material science doing laboratory automation, which means I have far too much experience making disparate interfaces talk to each other. And along the way, while I was learning about cloud programming as part of a coursework last year, I wrote a toy application, which we thought would be a great demo workload to use for these large-scale deployments. It's called Reporter, and it starts with a Raspberry Pi and a camera. Every so often, it takes a picture and it records environmental data, temperature, compass, and that sort of thing. It looks for objects in the image and it formats data. It then adds that to copies of the photo, turns it also into text, and then it sends it all to an endpoint out on a cloud server. And then it does it over and over again. So this is not something that's complicated for a Raspberry Pi. It's a pretty common sort of application. What made this different was that the whole thing was then packaged to run inside a Microshift cluster running in CentOS on a Raspberry Pi. And that was my big demo app for the end of my coursework. And it occurred to us that this is exactly the sort of thing that's a real app that would be interesting to deploy across a large number of edge locations. The problem is that it was written for a Raspberry Pi. And so if I put it, and they are in short supply. The supply is slowly coming up, but we needed to be able to deploy across simulators and virtual machines and other things. And if we look at what would actually happen to my existing app, run across different things, we get some interesting problems. If we run in a time zone other than the one I wrote it in, the data no longer matches to local sunrise, for instance, and that matters for environmental data. It'll run just fine on anything in a West Coast time base on a Pi with a camera. It won't run in a VM because the architecture is wrong. If you don't have the sensors or the camera, it can't run. The pod that talks to the camera will crash over and over and over. Won't run on an Intel processor. And in this case, it can cope with not having sensors. There's actually code that will emulate the sensor board, but without a camera, again, the camera pod will keep crashing. And in this case, the problem is that the time zones don't match. So there are ways to fix this. And first of all, I can make the code actually multi-architecture compatible. So I was able to do that. That solves the problem of not running on a Raspberry Pi, but it doesn't solve this camera problem. And at the time, we read some interesting discussions about what some of the large language models at OpenAI could do. And I was still learning how to write manifests. So the biggest problem was I couldn't put any logic in my manifest to decide which parts of my system to turn on and off. Kustomize can do it, but you still have to learn how to write the templates for Kustomize. I managed to do all that, but I wondered if there's a way to use a GPT-3 model and foundational AI models to help do that adaptation. So I'm talking about what I'm calling a placement configuration. It's deliberately a little bit fuzzy, but that means it includes the architecture, what peripherals are installed, and the environment, so time zone or anything else for a placement target system. So my goal was to write a simple text description of a whole bunch of systems of placement targets, and then run it through OpenAI's Codex model and generate custom manifests. So I didn't have to worry about it anymore. And, it's a little bit of a simple experiment, but it was really interesting to do. And in fact, it worked really well. So this video is slightly time compressed because the Codex large language model OpenAI was in beta and had rate restrictions. So I could only send a request about every 10 seconds. As it reads in my text description, turns that into a table, and then starts working through the different placement descriptions. The first one, the hardware is great, but it's in the wrong time zone. The second one, it's just needs to confirm the time zone. Third one doesn't have any hardware, so it's going to have to take out the camera pod. It's going to have to activate the replacement for the camera, and it's going to have to update the time zone. And it just keeps chugging through. It's not a complicated program. It's only 190 lines Python, and it just did the work. Now I had to do some advanced work in the sandbox for the model so I could learn how to make the queries that would do these changes. When it was all done, I could take the manifests and actually test run them on systems that matched the placement configuration I described, and was very pleased to discover that in fact they all ran the way they were supposed to. And I'm not going to make it go all the way to the end because it's another 2 minutes of our lives. I'd rather get back to you.
So Kevin, so you're showing how how that model was able to adapt each of the interface over and over again for the different locations and the different properties of the devices that were there. That's very cool.
Yeah, it's once I got it to work, I was amazed at how easy it was.
Kevin, one question. First, it's a very, very, very impressive demonstration. And the second question is, do you envision, or the purpose was to continue using, AI for any deployment, or it's just some initial configuration once you generated with the AI configuration for a specific kind of conditions, you store it somewhere and you will use that one for if that request will come? What is the vision here?
So this was a really preliminary experiment to confirm that working with a foundational model could actually do these modifications. However, what I would picture is as we're building KCP-Edge, we talk about locations. And so a location would include some of this kind of information. So as we're using our whatever form our control plane looks like, it would take advantage of that information to make these mods before it starts actually placing the workload on those locations. And as I said, some things you can solve by building multi-architecture packages. In other cases, you do have to worry about what is the physical hardware. So if your location record can include that information, so the control plane can make these customizations to turn things on and off. Sometimes you have to take things out of the manifest. In other cases, you can solve it by setting an environment variable properly.
Right.
But you need to know to do that before any manifest is actually used to deploy the actual workload to the target. The Kubernetes manifests don't have any logic inside them. So you have to customize the manifest before you use it. And so basically my idea was if we could do this, we then have to incorporate these calls before we do the actual download of, we have to customize the app manifest before it can go to the placement location.
So one additional question, not related at all to cloud or anything, but actually from personal kind of curiosity about, ChatGPT and OpenAI. Did you encounter with errors? Because we heard a lot about, mistakes and even quote unquote lies that those technologies kind of, I actually saw a question where ChatGPT kind of invented a character that wasn't in the book at all. So, did you encounter issues like that?
I did not, and there are some really important reasons I did not. That's a great question, actually. The first is this was not ChatGPT. This was using the DaVinci Text and DaVinci Codex foundational models rather than a chat model. I started with a master copy of a working manifest that worked on a fully equipped Raspberry Pi in my local time zone, and then used the Codex model to modify that. Usually that meant it might mean removing the deployment and service for the camera module, the camera pod, because if you don't and it can't run, it will crash and restart repeatedly, and eventually it'll take down your cluster, because the resource load of restarting it over and over and over again eventually will crash the cluster. On a VM, that's annoying. On a Raspberry Pi, that's a horror show because it takes so long for a Pi to reboot. So it was starting with known good code, and I was really, really thrilled at how well the Codex model understood YAML and manifest structure. So, yeah, I would say remove the camera deployment section, and boom, it was gone. Say remove the camera service, it was gone, and
Right,
it
so,
worked.
okay, just to be clear, right? And I think maybe to improve your presentation, maybe kind of a block diagram of, you know, training and inferencing and what information comes from where would help make this clear. But I think what you're saying, Kevin, if I understood correctly, you wrote some Python that tells the model, or it says what changes to make to the YAML, right? In kind of language form. Right?
Yes, and in simple language, because I am
Right.
still really new at dealing with manifests and all of this. So
Right. So my point is the knowledge that relates the characteristics of the location to what should be done to the YAML, that's in Python code that you wrote. You're using the AI technology to implement the plain English instructions for how to edit the YAML and actually do the editing of the YAML.
that's absolutely correct. Yes.
Right. You also use it in a separate step for some pre-processing of a table of locations, right?
Correct. So I wrote a paragraph describing a bunch of placement targets, and then it turned that into a table which pulled out the key components. That was actually harder to write than the Python to modify than the calls to modify the manifest.
So it would be interesting to try to use the AI to actually implement the Python. I think
You mean
it
to replace the
can,
Python, yeah.
yeah, it can give you something, right? It would be interesting to see what.
The way that this model works, you have to provide a basic instruction to start with, and then a modifier. So in my case, it was
Oh, okay, got it.
edit this manifest, which has these separators in it. I was using the standard row of hyphens as separators and sections for a Kubernetes deployment. So that told it what it was looking at, and then I could say remove this deployment, remove this service, update all of the time zone environment variables, and those, then it knew it was a Kubernetes style manifest, and it knew what I wanted to do, and it would go through and find it. And so it was, this was a limited experiment, but I was surprised really at how well it worked. And let's see, there are more details. I wrote a Medium blog post about this. Apologies that it's not a plain text link, but it is out there, and that includes actually the code and all of the sample manifest and everything. So if you want to see all of the gory details and what I did, it is available out there on Medium.
Can we be sure that you wrote the Medium and not your OpenAI kind of model?
Yes, because
Yeah.
I have a particularly nobody's told ChatGPT to write anything in my voice yet. I don't have enough blog articles out.
I was joking. Okay,
I
thank you.
understand.
That's a very nice demo. Thank you.
And just as Jun mentioned, our community is out there, and there's the barcode again for you to capture.
All right. Thank you, Kevin, very much. So what you can see by what Kevin just showed you, right, is this ability to use consistent declaration, have it modified somewhat automatically, and to cover a heterogeneous set of deployments or a heterogeneous set of edge locations, right, with different capacities, capabilities, time zones, maybe even sovereignty comes into play, and do this at scale. And one of the reasons why this is so important is that once we get to a certain level of scale, people don't want to manage these definitions by hand anymore. And so this is one way of exploring how we might take advantage of some level of automation to do that without writing endless numbers of templates for customization. So this is our repository, and this is our docs site for KCP-Edge. We're looking for folks to jump in head first and help us out with some of the areas where we're operating in terms of scheduling for Edge specific domains, in terms of summarization of status and collection of status. And you can go to our repository and click on issues and look up anything that has good first issue or help wanted attached to it. And those areas that the community believes that you might play a role in helping us get to the bottom of and design and build something bigger. So thank you very much for your time today. That concludes the demo day presentation. I'll have this posted to YouTube shortly. Thank you, everybody.
Thank you.